In this video, we're gonna go off topic. Instead of race cars, planes, drones, and so on, we're gonna talk about an overland truck, which is a truck which is usually modified to actually go on an off-road adventure. And the topic of today's video will be an overland truck created by Jay Jarvie, who runs the very interesting YouTube channel Build Creator. It's really cool. Some people are good at 3D modeling, some are good at building prototypes, some are good at clay modeling. Well, Jay is good at everything and combines it into his own projects. He has built his own supercar from scratch, which is really impressive. Just check out the videos on his channel, it's really interesting. And for his next project, one of the questions that he had, or that we discussed, is how can we make it more aerodynamic so that we can increase the range and increase top speed, reduce fuel consumption or battery consumption, and so on, depending on the drivetrain. So we started off with a reference, which is a default boxy overland truck simulation, which is this one. Generic one. I believe this is a generic model off the internet, and as we can see by the red pressure clouds, there's a huge amount of drag, all separated flow as it needs to curve around these sharp edges at the cabin, full of extremities, the mirrors, bars to protect stuff, boxy shapes, which is very practical but not very aerodynamic, and an indicative drag coefficient of 0.61, which is quite dramatic, especially if you compare it to a modern Tesla Model 3, which is between 0.20 and 0.25 or something. Now, for a truck, it's normal to be higher, but not so high is actually really dramatic in terms of the range. So we looked at the first design of the truck that Jay created. It's really interesting. And this is the model that we received for a first analysis. So we ran it through our simulation platform AirShaper. And the first thing that we noticed, if you go front to back, is that at the front we have sharp edges over here, for example, where the air hits the front, which creates a high pressure at the front of the truck. And then the air needs to curve around the car, overland the truck, via the top, via the sides, via the bottom. And when it goes via the sides, there's this very sharp edge here. And this is way too sharp a corner for the air to stay attached. So it separates and then reattaches further downstream. But in the process, it actually creates a lot of flow separation. A lot of vortices are actually originating from this point. So the air actually pushes upward, then tumbles down the side. And this creates a swirl as it goes via the side, and an opposite swirl on this side. So both vortices actually originate along these sharp edges. In terms of wind noise, this is even more dramatic, especially as this is very close to where the driver will be sitting. This creates a lot of wind noise. So this is one of the first areas that we agreed on to redesign for the next generation, actually the one that will hopefully be built. So then if we continue downstream, we can see that there are surface, like this one, for example, which is a hatch. It's very practical again, but if it's sticking out, especially when it has sharp edges, this generates flow separation. Another interesting area, again caused by a sharp edge, is this one here. So the air stays attached, is being pushed out to the sides of this cabin, and then plunges inward again as it reaches the underside of this cut. So this is a negative movement, let's say, an inward movement, and the curvature is too strong, so again the air starts swirling and leaves this vortex behind, which actually travels upward via the side of the truck. It actually looks quite similar to the vortex that we saw on the Tesla Cybertruck when we analyzed it. So sharp edges can be interesting, but you have to really watch out so you don't create the wrong vortices and flow separations. So this hatch, if we can make it flush, that would be really interesting. Another thing are the wheels. So we see that the airflow stays fairly nicely attached at the bottom here, so it's a nicely inclined surface pushing the air downward. But then at the bottom, wherever you do have open space, like the wheel wells, you will get flow separation. And these massive exposed wheels with a lot of tire threads spinning like a mixer in the air really generate a lot of vorticity, turbulence, drag, and so on. And again, cleaning up these edges where the air again needs to curve around an edge, that would be interesting if it's permitted or possible given the structural frame which is inside. Then at the back here, same story. Air hits the wheels. Quite a dramatic effect on the airflow. So whatever we can save there would be nice, but the clearance is a given. So maybe some dynamic ride height changes could be an option in the future, but that's quite expensive usually. But for now, we're not going to focus too much on the wheels. Instead, we're going to look at what happens at the top of the Leviathan. So we have this, again, very practical shape, very good for structural components to weld the frame on the inside, but the sharp corner between the horizontal top of the roof and this inclined shape that actually closes the overall shape of the Leviathan is a sharp one that triggers flow separation. Very interesting to see. You even see some flow patterns similar to the Ahmed body, which is actually a validation case for automotive objects. Long way back, it was designed. You get some flow separation here. The flow tries to reattach, and also in the horizontal plane, the air is trying to curve via the sides into this low pressure vacuum almost. It's not a real vacuum, but low pressure area left behind the central tunnel. And again, as the air curves around this edge, trying to make this way inward, you get again a vortex there and flow separation. Same for the overall air, trying to curve around the edge of the truck to join the air at the more central area behind this truck. So again, strong vortices which usually indicate loss of energy. This is the total pressure coefficient, which is an indication of the energy or energy loss you have within your flow. So the cool thing is that Jay went to his designer and asked him to implement some of these changes, and we had a drag coefficient of 0.5 for the first iteration, which is already pretty good to begin with compared to 0.61 of a default truck. After the changes were implemented, we were actually at 48 in terms of drag coefficient. So a 4% drop, that's not an insignificant. That's actually something you will notice in terms of range. Because aerodynamics at high speeds can be responsible for over 50%, sometimes even 70% of your fuel or battery energy consumption. So reducing it by 4% might actually increase your range by perhaps 2 or even more, 2%. So that's really relevant, especially if you can do it with some small changes that don't really cost you anything. So at the front, we can see that the flow has been cleaned up. If you compare it to the previous one, this one was really edgy, lots of flow separation. This one actually has a much reduced flow separation area. We still have some vortices, especially around this area, which remained fairly unchanged. Also, what we did is that Jay, or his designer, added a deflector in front of the wheels to actually push the air downward a bit more so it doesn't hit the front face of the tires full on and actually splashes out a bit more left and right. So this is what you see here, the difference between the wheels. Of course, you still have pressure on the wheels, which is normal, but the pressure pattern here has actually been pushed downward compared to the original truck, where you don't have the air deflector and the air hits the tire at a higher area above the ground. So a higher pressure pattern there, a high pressure pattern. So that's really interesting to see. And then if we move to the back of the Leviathan, we can see that they added this nice round here because this was a different construction method compared to the front. This was more difficult to modify. This one could be modified. I think it was made up more out of composite materials, so more freedom in terms of molding and so on. So this round shape now makes it possible the float to stay attached, which you can see by the surface friction to some extent. You now have nicely parallel streamlines here. They still curve inward because of the air joining from the sides, but compared to the previous one, you could see that we had flow going in different directions, also outward, and we had this blue patch here, which indicated flow separation, which we don't really have to a much lesser extent actually on this design. And you can actually see this replicated in these let's say pressure clouds is what we call them. So the original one had vortices around the side edges, and this one separation bubble, not too big, it wasn't too dramatic, but still it was there around the central area. And this one features a much cleaner airflow around this central tunnel. So with a few small tweaks and for an unexpected application as Leviathan, we were actually able to help Jay to cut drag by 4%, which is quite significant. So for sure, there will be more modifications to come, and we're really interesting to see where it goes with this fantastic project. Do check out his channel. Really interesting to see what he's working on, which techniques he uses. Try to copy some of it, the techniques, not the project, obviously, in your free time and build your own dream. Still, last but not least, a massive thanks to Jay for being so open to collaborate with us. He has a separate standalone video on his channel, so please do check it out, where he explains the aerodynamic process from a user perspective, how he got to upload the model to AirShaper, what he liked, what was a challenge, and so on. So check it out. Check out the other videos on his channel. Really interesting. And thanks a lot for watching. See you soon. Stay tuned. Bye bye.